Okay. And so the answer to that one right here was, oops, this right here. So you would, of course, figure out the number of electrons first. Then you'd put the negative charge on the whole thing. And then what you would do is put single bonds in, put the electrons around first, and then you'd move electrons into double bonds until you have everything full. Notice one double bond will fill up the carbon. So for example, it was very obvious which ones were wrong just by the number of carbon bonds on that previous problem, right? Like that alone solved it. Yeah. And that's true for most chemistry problems, really. If you step back, you can usually solve most chemistry problems, or at least figure out if you're wrong on most chemistry problems by really simple principles, right? It's don't need to know the whole thing. All right, so not all atoms are going to have a complete valence shell, and some are short of an octet. For example, boron. This is very, very common. It will almost never have an octet. In fact, it's very rare for it to have an octet. And so here you're actually seeing an example of that only has 6 electrons, right? So not an octet. Why it only has 6? Well, it only has 3 electrons to contribute to bonds. Okay. Now, is boron quite reactive? Yes, it actually is pretty reactive. So it being stable like that does not necessarily mean it's like 1,000 years of the same thing and going to forever be boron with 3 hydrogens, and it can never do anything else now. Same thing right here. This is a carbocation. So it's lacking an electron. It lost it. It has a positive charge on it. It's very reactive species, but the most stable form of it that you can write is that. Okay? And so that is what the lacking octet. This one right here actually has an expanded octet, and that's sulfur, and that can happen because it's on the 3rd period, right? Anything on the 3rd period has d orbitals available. They're not usually used. They're high energy. This would be pretty reactive, okay? But it is available. You can fit electrons in it. Okay. One of the things you guys all have to like back off from your general chemistry, you kind of have to reteach yourself, is that acidity, basicity, stability are very different things in organic chemistry, okay? So organic chemistry, we'll talk about bases that you wouldn't even call a base in general chemistry. Okay? We'll talk about acids, things being acidic, and you're like, this is more basic than the strongest base in general chemistry. What are you talking about, Dr. Clausen? But remember, it's a relative thing, right? And so if we have a stronger base, then whatever the weaker base is, it could be an acid, couldn't it? Okay. Okay. And remember, 3rd row and below, you have the d orbitals, even though they're not used until the 4th period, right? All right, so this right here is your normal number of bonds. Right here is your normal number of lone pairs. And right here are your examples. When you hear rules that I give you in organic chemistry, what I want you to think of is they're like the laws in society. Okay? Your law says you can't go over 55 on the road. Do you ever go over 55 on the road? Yeah, you all do. I know you do. Don't even try it. You all did. And so organic chemistry, there's going to be a lot of things. There are going to be rules and laws. And for the most part, they're followed. But there's a lot of these things that there are exceptions. How many electrons are in a bond? 2, right? That's the rule. Not all bonds have 2 electrons. You can make bonds with 1 electron. Okay? They exist. Brandt's rule, they found exceptions for it recently. Like organic chemistry is one of those things people love to find rules that they can break because it makes whole new fields of compounds you can make to, do drugs with and everything else. New materials for you to use on your phone screen, right? New OLEDs. Anyways, this is the general rules again. Is everybody comfortable with that? You notice just the same rules we talked about before and you've seen in general chemistry. Okay, so covalent bonds, these are going to be characterized by sharing electrons between two atomic nuclei. If the atoms are identical, then the electrons shared have to be a nonpolar covalent bond, meaning neither one is going to pull the electrons more than the other, right? And so the electrons are exactly equally split, and you don't have any overall charge. If the atoms are different, then one nucleus is going to attract the electrons differently than the other, right? Meaning one nucleus is going to pull those electrons more strongly, one less strongly, right? If the electrons spend more time on one side, what's that going to do? Negative charge, right? And so a polar covalent bond is polar, meaning it has two poles, positive and negative sides. Okay? And which one's the negative side? The one that holds on to electrons better. Anybody remember the trend for that? That's electronegativity. As you go up and to the right, electronegativity increases. What's the electronegativity of neon, by the way? There is none. You got it. Yeah. So the electronegativity of fluorine is 4, for reference. And by the way, does anybody know why fluorine is 4? Because a chemist wanted to finally have a 4.0 when he got an F. I'm not joking. That literally is the reason. They just set 4.0 so it could be grading scale 4.0 F. Goodness. Oh, man. This is why we name things what they actually are usually. Our jokes are terrible. Okay. But neon, argon, krypton, these things don't have electronegativities because they don't typically take place in bonds, right? And so electronegativity is how well you hold on to electrons in a bond. Okay. So the ability to attract electrons in a covalent bond, again, this is going to be called electronegativity, is denoted by capital En. This is actually the table of electronegativity. It was originally set as a 4.0. I find it very ironic that they, of course, got the number slightly off because they couldn't calculate it. And so the actual number is 3.98. So that damn F brought our grade down. No. Yep. Do note that like krypton does actually have an electronegativity. You can force bonds with krypton. Okay. And so like your normal rules again, we're violating those rules, aren't we? Yeah. If you take fluorine, you can actually bond to krypton, and there's a few other things you can do. Like that carbocation I showed you before, you can do some stuff with that. Anybody have any questions so far? Okay, fantastic. Okay, so your covalent bond, the electrons are likely to be found near the nucleus of the more electronegative atom. They're going to spend more time around that. That's usually a better way of thinking about it because they're going to be more strongly attracted there. Okay. And so the electronegative atom is less likely, they're less likely found around the less electronegative atom. The more electronegative atom, they're more likely to be found around, or they spend more time around. And so your less electronegative atom has a partial positive charge. That's what the small delta means there, by the way. Partial, and then positive. Okay. Small delta, partial, negative charge. Okay. Not full charges because we don't wholesale lose an electron to the other, right? We're only sharing them, okay? Right here, this is another way of representing that. Plus, where the positive charge is, arrow towards the direction the electrons tend to go, okay? This right here is just a bunch of polar bonds right here and showing you some various bond dipoles. So this right here is a polar covalent bond, okay? And it has an overall polarity to the molecule. Can everybody see that? There's an overall positive and negative end. Okay? And so it is a polar molecule. This right here, on the other hand, CH4, you see that these have little arrows. And they're all going in. So the carbon's going to be a little negative. The hydrogens are all a little positive. But it's symmetric, isn't it? And because it's symmetric, that means you have positives pulling the exact same amount in every direction. If you pull something the exact same amount in every direction, is there going to be an overall charge? No. And so that's a nonpolar compound. Okay, this one's also a nonpolar compound. Again, you see the bonds are polar, aren't they? Okay, but they cancel each other out, don't they? And so nonpolar overall. Now, these polar bonds, these are referred to as the bond dipole. Dipole meaning two poles on your bond, right? And so these are our bond dipoles right here, 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 here. That's also a bond dipole, but a molecular dipole as well. Okay. This is both right here because there is no others. Yeah. So you only have the one bond dictating everything, right? These ones have no overall molecular dipole, and so they're nonpolar. Anybody have any questions about that so far? Okay. Now, there's a couple things that is going to be involved in these bond dipoles. These difference in electronegativity between the atoms involved is usually the biggest one that you're going to most need to know. Okay. So that's the differences right here where we're seeing those differences in electronegativities. Okay. Right here. And so difference in electronegativity between those will mostly determine the bond dipole there. Okay. There's a few other factors that have to do with essentially the geometry. Okay. But you're just never going to need to know that unless you got a lot more chemistry in your belt. So, and at that point, the extra time's better spent on other things. Let's identify the most polar bond in this molecule shown here. We're going to draw a dipole arrow along that bond to indicate the direction in which the bond dipole points. Okay. So how do you do this? What's the most polar bond going to be? Exactly. The biggest difference in electronegativities, right? And so we're going to look these electronegativity values up, figure out what the biggest difference is between them are, and that's going to give us where our bond dipole is. Now, you can save yourself some time and effort because carbon is going to be the ones we have to look at the most, isn't it? See that? Hydrogen and carbon is not going to be that big of a difference, right? So we can ignore those. Really, all we have to look at is the lithium versus carbon versus an oxygen, don't we? Okay. Now, typically, metals are going to be your bigger differences. And going up and down periods, especially in the first two rows, tends to be large differences. Okay? So, like, I'd look at the lithium first if I was going to do this. Then at the oxygen. Okay? Okay, so which one is it? Yeah, lithium carbon, you got it. That has the biggest difference right here. The positive charges at the lithium, right? Where's the negative? The carbon. You got it. You got it. This one's actually a pretty big difference. You see that? Note that you can have partial charge differences that are full charge differences or more. Okay? I actually did, one of my publications is on a compound that has a 4+ charge at the center of it with no overall polarity because it's all surrounded by stuff that withdraws electron density extremely well. Yeah. So that middle gets very positive. It can do some cool chemistry, but you can't get to it easily. So you can kind of control it. Right here, we actually see electrostatic potential maps. They're just mapping this difference in charge. So right here, we have a really big difference. And you see there's almost a full charge difference. Okay, this is really close to being ionic. This right here is lesser differences. And we have some, different structers here. We have double bonds that cancel out. So we have no overall dipoles. There's our boron again. Which is kind of neat. Note that boron's kind of cool because it's actually positive for boron. Boron actually has less electronegativity than hydrogen. So it's one of the ways you can make a negatively charged hydrogen. Ooh, foreshadowing. All right. I know this is a literary masterpiece here. Okay, so the elements in a compound have large enough differences in your electronegativity. Ionic bonding will occur, or can occur is probably a better way of saying that, actually, because it actually needs to lose the electron, which sometimes doesn't happen right away. So right here we have a metal with a nonmetal. This is going to be the vast majority of ionic bonds. You can get ionic bonds with nonmetal, and you can get ionic bonds, covalent bonds with metals and nonmetals as well. But they're very rare, much rarer than metal and nonmetal equals salt, which is what you've probably heard before. Right here's some examples of these, right? Where we lose an electron from sodium to the OH minus, and that is sodium hydroxide, isn't it? Yep. Anybody do tie-dyeing? That's that lye. There you go. Potassium, right here. Anybody have any questions so far? No. Has anybody ever seen a drug that has like .HCl behind it? That's this, actually. So you've mixed a base with HCl to make an ionic, so that when it goes in your blood system and you take the pill, it can go into your blood system easier. In your body, it typically gets converted back to neutral at some point, and that will then absorb it through your cell membranes. Yeah. So they're playing games with the polarities of that. Okay. Or the water solubility, I really should say. So how do we assign formal charges to these? So how do we assign those electrons to each of these atoms? So we determine the charge of an atom in a molecule when the electrons make up covalent bonds or shared between atoms. One of these ways is the formal charge. This is the one you probably remember from Gen Chem, I would imagine. There's actually a couple other rules that we'll discuss throughout this semester / next year as well. But this is probably the most common. However, keep in mind formal charge, okay? You got to remember that definition now, because we're going to have some things that are similar. All right. You assign the electrons to your atoms. Notice that's the same way we had talked about in terms of figuring out what the Lewis structures were. Okay. You compute the formal charge by comparing the number of electrons assigned to the atom's group number. So how many did it gain or lose from the element on the periodic table? Okay. That's all this is. So right here, we have 4 electrons that are assigned to it. This has a formal charge of 0 because its group number is 4, right? Okay. And the reason it gets 4 electrons assigned to it is we count the number of bonds, and that's the number of electrons assigned to it. Okay. Or another way of saying that is we count the number of electrons and divide 2 for any of the iron bonds. That's the same rule, it's just more steps. All right. Up here, notice we have 1, 2 bonds, and then we count anything that's not in a bond as belonging just to that atom, because it only belongs to that atom, right? And so 1, 2, 3, 4, and then an extra 2 in the bond, that's 6. And so there's 6 electrons. We look up at oxygen, group 6. Difference between those is 0, isn't it? Okay. Let's go ahead and look at something with a negative charge. Here we have 7 electrons that are assigned to this oxygen. Its group number is 6. And so we have 6 minus 7 gives you -1 formal charge. That making sense so far?
So that bond is represented as 1 electron.
Yep. All bonds are always represented as the number of bonds is one way to say it, or the number of electrons in them divided by 2. Okay? And anything that's in lone pairs that's just on that one atom, you just count those straight up. Okay? Or another way of saying that is the number of lone pairs times 2. But hopefully nobody goes through all those steps. That's a waste of time. Anybody have any other questions? Okay, so let's talk about localized and delocalized electrons. Hopefully that's a little familiar. Some species are not going to be described well by Lewis structures because the Lewis structures imply that all electrons are localized and cannot shift and denote. They're going to be confined to a specific region in space rather than being able to move around. Okay? Remember that in reality, this is what we're really looking at and denoting, right? these electrons are not stuck right there, are they? They can get pulled over to here. See that? Which is that on? Both, isn't it? Yeah. And so in reality, when we talk about real structures, when we have delocalized electrons, we're oftentimes going to have to do something called making resonance structures. You guys may remember this once I flip on to the next deal. But remember, first off, delocalized electrons. So delocalized electrons are going to be things like lone pairs and double bonds that can move around because they're not contained directly between two atoms. Localized electrons are going to be things that cannot move around, like a single bond. That can't move around. It has two things on each side. It's contained within that. Okay? Okay, let's look at some resonance structures right here. Here we have two possible structures we could have written as Lewis structures. Okay, notice they're really the same structure, just changing the oxygen, right? Yeah. And so we could have brought these electrons down into a double bond, or we could have brought that electron down into a double bond, right? Yeah. Is either one more valid than the other? No, that's just silly, right? They're the same thing. I think everybody can just very easily see they're the same structure, just flipped, aren't they? Are these actually different? Yeah, they are. Like geometry-wise, it's kind of like you have the pencil in your hand, if it's left or right, but it matters for your writing, which side it is, right? So what we're really seeing here is these are actually like 1.5 bonds on each of these, okay? They're sharing the electron density, right? And so we represent the actual structure with this right here. This is a resonance arrow. It means that the actual structure is a combination of these, okay? It's a little bit of double bond character, a little bit of single bond character on each, okay? And that's what the real thing looks like. We couldn't represent it with our single double bonds, could we? Okay? Is everybody okay with that? Okay, you starting to remember that from Gen Chem? Yeah. Okay. So this is actually more like what it would look like. This would be a resonance hybrid right here, where we're sort of writing it out with some symbols to try to represent that better. But oftentimes your resonance structures are actually a better way of doing this because you can more easily see reactions. Okay? Like you can see very obviously one of these oxygens can attack things with its negative charge really easy, right? It's going to be reactive. Okay? They both are, but being able to see at least one of them is helpful. Okay, so right here we have a duck otter and duck-billed platypus. Kind of like a resonance structure, right? I know, that's such a chemist way of saying things. Totally isn't. I know that. I do have one credit hour away from a biology undergraduate. I know that. But this is funnier. Haha. Okay. So let's talk about resonance structure stability. Now, resonance structures are going to be lower energy, more stable, just like if you think about lifting and carrying your desk. If you lift it with just one person on the edge, it's harder to hold, right? You lift two people, it's easier to hold even if they were only half as strong, right? Or another way of thinking about that is like you can lift it in the middle and it's easier to carry, right? Lifting at the very edge, it's really hard to carry, okay? And so resonance structures provide stability. When you see multiple resonance structures, it actually stabilizes your structures, okay? Because they're sharing the load of those electrons among several atoms. Now, more atoms with a complete octet is going to be one of the reasons that you typically get lower energy, more stable structures. Fewer atoms with non-zero formal charges is also another reason. Remember, you're splitting up those formal charges too. Okay. A -1 formal charge appearing on a more electronegative atom and a +1 formal charge appearing on less electronegative atom is another reason. We see here this positive oxygen there that would not be very stable normally. And so what we actually seeing is this actually contributes less, this contributes more, but they do share the electron density there. Okay. All right. Mm-hmm.
About that, like, structure, why? Because doesn't Artemis have 4 bonds?
And in this case, we can't make 4. So we can't make 4 without violating another rule, which is that your formal charge should always be on the least electronegative if it's a positive formal charge. And so what we end up doing is, this is one option, of course, right? And that makes the 4 bonds. And so we fill that rule. But then we're messing up the rule. We're putting a positive charge on oxygen, right? Which oxygen is more electronegative. It's going to pull those electrons, isn't it? And so by taking the resonance structures, remember the actual structure is both these together. And so what we really have is a double bond, but that double bond has a lot of that positive charge on carbon and causes a bit of positive charge on the oxygen. Does that make sense? And it's not quite a normal double bond. It's more like a 1.5, 1.9 sort of bond. It doesn't share its electrons equally. It doesn't really have those electrons staying like it would normally do in the p orbitals. Okay? Is that making more sense? Yeah. Yeah. Okay, so the resonance structures is going to be stabilized as a result of the delocalization of those electrons. And that, so whenever you're looking at resonance structures, the places you're really looking at is delocalized electrons, okay? Lone pairs, negative charges up in lone pairs big time, okay? Double bonds, triple bonds, because these are delocalized, okay? The double bond and triple bonds are delocalized, not the single bonds. Okay. So the resonance structure here is going to have your electrons that are localized here. Then we have your resonance energy right here, and that's representing the amount of energy that you're dropping by having those delocalized electrons right there in the red shared between the two. Okay, and you'll notice it's a pretty good chunk actually. This is why, for example, phosphate are the backbones of DNA. They have a huge chain of resonance structures actually. It's 4 or 5 depending on the structure. Okay. So phosphates are highly resonance stabilized. If that wasn't true, phosphates would actually be very reactive. Your DNA would like blow up all the time, which is a whole another idea, right? I mean, think about that, right? Look at phosphorus and oxygen. They're pretty far apart in terms of electronegativity. And then you have 4 oxygens on a phosphorus. Like, that shouldn't be stable normally, right? It sounds pretty crazy. And it is. If you don't know about resonance structures. It's this resonance structures that's bringing that structure down. Yep. Spontaneous pow. Okay. There is actually some funny stuff you can do to cause DNA to become super reactive. It's, for example, why you can make like gun cotton. That's not DNA structure, but you can react things to set them up to be very energetic. Yeah. So, pow. All right. So a species that has equivalent resonance structures tends to be highly stabilized. As the number of resonance structures increases, the species tends to be more stable. This is actually benzene. Has everybody seen benzene before? 6-member ring. Usually there's like a little circle in it. That's actually denoting this structure here. You put a circle to represent the 1.5 bonds. Note that this benzene structure shows up all the time in pharmaceuticals, by the way. If you were to look at pharmaceutical brands and logos, you'll see like a 6-membered structure with a circle thing. And you'll see it like half cut, quarter cuts, all sorts of weird stuff. Because very, very biologically relevant structure. At least in terms of like making drugs for people. Yeah. So these are non-equivalent resonance structures right here. Notice that if you go to this other one here, you end up with a negative and a positive charge that are separated there. And so formal charges that are separated. So this is a very small contribution to your hybrid energies. It's not going to help you gain a lot of stability because it's just very high energy structure. Okay. And so these are non-equivalent. You may have noticed I already hinted at this before when I was talking about the other structure with the positive charge on the oxygen. I was like, this one's less stable. This contributes less. So we would expect this one to look mostly like this and then a little bit like that. Okay. And so you'd have a little bit of charge there. Right? Okay. Anybody know what that is, by the way? It's formic acid. As in, like, well, you guys have probably smelled it because some of the formate or formalin has reacted with acids and oxygen in the air and made formic acid. But usually Asian beetles and ants will spray it on you. And that's what you're actually feeling, not a bite for a lot of those. And it actually tans human flesh. It smells kind of like freshly cut grass. Thanks. All right, so this right here, some strategies for success when you're drawing all the resonance structures. Any two resonance structures are going to differ only where the electrons are located. So your atom itself has to be frozen. Your nuclei can't move around. Your localized electrons will also not move around, i.e. the single bonds. Okay. We represent the movement of the electrons by use of our curved arrows. This right here, see, it has a 2 tine on it. Anybody know what tine is? You know how the arrow comes down and point things? Each of those is a tine. Okay? Like you can have 3 tine arrows where it has 3 points coming off. You can have 2, 1. Yeah. The ones you most often see are 2 tine. This means 2 electrons are moving. Okay? If you have only 1, a half arrow, that's going to be 1 electron. Okay. And so we're moving the electron here into this bond. Notice that's going to give us a double bond. Now, let me ask you a quick question. Can you reach her tablet? No, you can't, can you? And why can't you? Too far. Even more specifically, there's people in the way in there. Yeah, you just can't do it. And you can't reach her book, can you? Too far. Too many people in the way, right? Well, remember that these electrons, when they're moving around, there's electrons here, right? So if we try to move through this carbon, there's electrons there. I can't move through it, can I? It's just not going to work. Like, it's physically impossible. You already knew this. That was pretty obvious if you thought about it as anything other than chemistry, right? But you're going to think about it as chemistry and you go, I don't know. But remember, it's still physics, right? Yeah. So the electrons can really only reach the bond or the atom next to it. And that's it. Okay? If you put an electron on a bond or atom next to it, what's going to happen to the electrons that were on that atom? Yeah, like billiards, right? Ball hits another ball, boom, it's going to move over somewhere else, right? And so our delocalized electrons are going to hit each other and go into another structure. Typically, you go all the way to a structure that makes sense to be somewhat stable. But in the homeworks, they're going to do partials, right? Because they're going to want you to do like the pieces, understand it a little more, right? How do you know where you're supposed to stop? They tell you the next one. Okay? And so they tell you the next one, right? To get that from that, what do we have to do? Well, we have to make a double bond. So this has to go into the bond, right? The electrons in this double bond have to go up onto that oxygen. Okay? Is it the same thing to take the electrons from this bond and put it here? No, that would actually cause a negative oxygen just float off. Right? Very different structure. Really high energy one, too. That would be a boom moment. Yep, that's your sugars going boom. Okay. And so electron into the bond here. This double bond goes up onto the oxygen. That's going to then be a negative charge there, right? If you take, let's say instead we go ahead and move this onto the carbon. What would that do? Wouldn't be a double bond, would it? That would be a lone pair negative charge on there, wouldn't it? Yeah. So keep in mind, like, it's actually just physics, right? Like normal physics. If you give somebody a pencil and share it, you know, you both have the pencil that you're using back and forth, right? If you just give it to them completely and say, yeah, I'll go get another pencil. Well, then they have a different pencil, right? Okay. Anybody have any questions there so far? Yes, yeah. Those would be equivalent structures right here. And they'd have an equal contribution. So this is actually the case we saw before, where we actually had like the, remember the charge that went like that? That's that one. Yep. So those are equivalent ones, and they equally share those charges. Okay. So let's talk about some of the features that indicate another resonance structure. Feature 1, a lone pair on an atom adjacent to a multiple bond. That one you've seen quite a few times now, right? We have a lone pair here. It's right next to a double bond. And so that indicates that you're going to be playing billiards, doesn't it? You're going to have an electron going over, making a bond, and that's going to make a negative charge over there. Like that. Another indicator is a positive charge next to a delocalized electron. So a lacking octet. Something that doesn't have a full octet, and then you have delocalized electrons next to it. Okay? And so what that means is you have an open magnet trying to pull those electrons over, don't you? Okay? It's like the partner next to you getting grabby and grabbing your pencils. They might get a few. Okay. And so feature 3, the atom with a lone pair that's adjacent to an atom that's lacking an octet. This is, again, just delocalized electrons next to something that lacks its octet. Now, when I say octet here, remember that that is actually noble-like configuration. So it could just as well be a positive hydrogen, in which case we're looking at an acid-base reaction. Or a number of other cases that are similar, right? It could be, for example, something lower period that's going to be an extra octet. Okay. Okay, another feature that might indicate a resonance structure, polar multiple bonds. So right here we have a very polar double bond. And so you have a contributing resonance structure where you just have the charge on the negative, the more electronegative atom has a negative charge. Less electronegative atom has a positive charge, right? Okay. Now, one of the things is a ring of alternating single and multiple bonds. Because it's a fully closed ring, it can make a circuit, can it? And it will. It's a circuit, just like a wire closed around a battery, right? It's just a circuit. And so the electrons can flow over one step. Okay. And so you'll just get the benzene-like where you go one step over, and those are the new double bonds. Okay. And because the circuit closes, they're going to be energetically equal. No problem. Okay. Okay, so how do we approach drawing all these resonance structures for a species? Frequently, a species is going to have more than the 2 resonance structures. It's not uncommon by any means to have like 4, 3, 5. You can have 20. Like these things can get really crazy, but that's very large structures. Mostly will be small, and maybe you'll get an 8 or 10, but that's per average. Okay, and so right here, we actually have a negative charge at the end. Everybody say okay? And so basically what you can do is just move that into a new bond, and then the double bond goes over, makes a new negative charge, can't it? Yeah. And you can do that for each one over and over. Okay? And you just go through, and those are the 4 resonance structures for that. Did everybody see why I could do that okay? Okay. Keep in mind, it's not going to end up on the carbon next to the other carbon. It's going to skip one when you do these. It's a very common mistake to make, where you guys will try to put the negative charge here instead of over here. Okay? It's just, you get bored and you stop thinking about it. Yeah. All right. Shorthand notations. So when we're learning organic chemistry, you're going to draw many, 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 many numerous molecules, and it's going to be a lot of drawing. Congratulations, we finally got art class. Yay. Okay. To say, by the way, organic chemistry is one of the most imaginative chemistries. If anybody ever tells you that chemistry doesn't have a lot of like art in it, it does. Okay? There's tremendous amount of art and freedom to make whatever you want, however you want. You just have to learn a lot more tools in chemistry than you do for a typical art class. Okay? That's really the difference. It's just a lot more learning before you can actually do anything. So you need to learn how to draw these in such a way that you're not sitting there trying to do a Lewis structure for 20 atoms. It's just not going to be feasible to do that over and over, right? I think you all realized that pretty fast from the homeworks. We use chemistry shorthands to save time without losing the structural information. And so what we do is partially like this is propane, right? And this has very little information about it, but it does have a mostly complete indication of what this is, okay? And then you can write it out like this, and this is another shorthand. And so you list the thing that's bonded to, the thing that's going to fill in around it, the thing that's bonded to make a complete chain, right? And we just keep going along. Can everybody see okay? Okay. And so your carbons are like your main chain, right? Your skeleton of your structure. And then the hydrogens just really fill in around it, don't they? What you notice about this, though, like, how do we know this is bonded to that? How many bonds should carbon have? 4, right? And so carbon has 3 around it here, right? And so we have 3 of the bonds filled. How do we know this carbon here doesn't bond to that hydrogen? Well, hydrogen wants how many bonds? 1. It's already full, isn't it? Carbon, on the other hand, we're lacking a bond, aren't we? And so this is bonded once to that one, isn't it? That fills in our 4. Okay? We have 2 more hydrogens, so 2 more spots get filled in, with 3's filled so far. 4th one is that carbon is single bond. Can everybody see how you can rapidly go through this? Once you're used to it, you just will know. Okay? What if I only had 1 hydrogen on there? Yeah, I have to have a double bond, don't I? It's the only way I can fill in my 4 bonds. Yeah. And so we saved ourselves a lot of time writing that out, didn't we? We can indicate most of what we need. Yeah. Okay, this right here is then more of a Lewis structure type of formatting, though we haven't like expressly done all the electrons. Okay, and so we write the carbons, we put in the high single bonds to each thing. That's actually a spelled out structure. Okay, that's a longhand. Okay, this is considered longhand for chemistry. Okay, this is condensed, by the way, in case you're wondering. And then that's just the IUPAC name. Okay, so again, these are the formal charges, and what you can see here is you can kind of help yourself out here because you know the number of bonds everything wants. You can actually make your life a lot easier. So if you have a -1 formal charge, you have 3 bonds around a carbon, you have 2 bonds around nitrogen, 1 bond around oxygen, right? Because the negative charge means we have an extra lone pair, takes it up. The zeros are those normal numbers we had talked about. That's the periodic table counting. And then this is +1. And what we end up doing is, again, we're going to have an extra bond for most things, except if we're in like carbon, right? Because then we get the same issues as boron. That's why I typically talk about it in terms of periodic table, is because you literally can just shift over boron, right? 3 bonds around it, just like boron. Okay? And that's another way you can easily just pop these off and know them right away. Okay? This class does have a bit of a time constraint, so keep that in mind. That like if you take 3 hours on a single homework assignment or 6 hours on a single one, you aren't going to have time to get everything done, right? Yeah. So you should take maybe 3 hours on assignment would be a pretty reasonable thing as long as you're learning a lot on it. It meant you probably had a little difficulty on it, but not too bad. Okay. If you're getting up into the 4 or 5 hours, you really need to like get some help and talk to your professor and ask questions. Okay, because you need to be somewhat efficient on your time, unless you can just stay up all the time and do everything. No, don't do that. I'm joking. That's a joke. Okay. If anybody was like, yeah, it sounds like a good idea. I don't need sleep. All right. Condensed formulas are going to allow us to include molecular and molecular ions as regular text. So this is going to be an example of condensed formulas here. Here we have a condensed formula. And see how we've put CH3 in parentheses here? That's indicating it's jutting off to the side. It's not included in the main chain. Okay? We've separated it out. Is that making sense? Right here we have ethanoic acid. Again, see how we have these oxygens here? We don't really indicate their bonds, but you can figure out pretty easily by this carbon used 1 over here. So it has another 3. And so there has to be a double bond and a single bond there. Double bond to one oxygen, single bond to the other. Fill in that oxygen with a hydrogen. Okay? And again, see how we just using those numbers of bonds again, aren't we? Okay. Okay. This right here is going to be line angle structures. Sometimes just called line structures because people get lazy, which fair enough. That's like half of chemistry. People got lazy. But line structures, these are going to be similar to condensed formulas. They're going to be compact and they can draw on quickly and easily. You guys will note that there is a tool on many of your tool sets for the online homework that looks like this. That tool, actually, if you take it and click it, you can then drag out the structure you want. So like, let's say you want a chain of 6 carbons, you can use that tool, click it, and then drag out 6 carbons. Okay? And you can kind of like modify it and change it the ways you want. You can also use that tool to just click in the same place over and over and keep adding carbons out. Okay? Okay, so this right here is a line structure. What do you notice about that line structure? What are all the angles? Carbons. Yep, every angle is a carbon, right? Because it's literally carbons are our chain links, right? We're making that chain. Okay. Where'd the hydrogens go? How do I know the hydrogens? Yeah, everything adds to 4, right? So that carbon there has how many hydrogens? 3 to get to 4, right? That one? That one? 2. You all fell apart for a second. It's the nitrogen, wasn't it? Dun, dun, dun. What if you have an oxygen, nitrogen, chlorine, anything but a carbon, but it's not hydrogen either? You're going to write it out, aren't you? Yeah. So you put a line for the bond, right? And on the other end of that line is whatever it is, nitrogen in this case. Okay? Is there a carbon right there? No, there's a nitrogen, right? Okay. How about there? That's still carbon, isn't it? Okay. Typically, you go ahead and write your hydrogens whenever you represent the oxygens or nitrogens, okay? By convention, because those tend to have other things that can happen, okay? And very often. Right? You may have noticed that if you take any biology, stuff happens to the nitrogens and oxygens a lot, doesn't it? Yeah. Okay, these again, see that's a double bond there. On this end, there's 1 carbon, right? On this end, there's 1 carbon. How many hydrogens are attached to that one? We have 2 bonds accounted for, so the other 2 is hydrogens. Yeah. How about there? There's 1 hydrogen, and that's a triple bond, right? Yes, typically, and we'll get into it when we get to like organometallics. So normally metals don't make covalent bonds, and so you don't really have to think about it. But actually, in lithium's case, you can. Yep. We don't do that for lithium or anything else because hydrogens fill in all over the place for organic chemistry and for biology as well. But lithiums actually have some really weird chemistry. If you have a lithium, you really need to know. Does anybody know what organolithium does to people? It's a psychosis medicine. It completely changes your neural brain pathways. Yeah. If you don't have schizophrenia, it would give you schizophrenia. Okay. And a bunch of other stuff, depending on the doses and how your brain handles it. It is like people that have schizophrenia and take lithium, it's an extreme medicine to take. And they know that they need to stay with their doctor 24/7 and keep on track of that and report any issues, because lithium is a very powerful psychogenic, psychoactive drug. It's actually amazingly powerful. So if you ever have lithium on a structure, tell people. But yeah, anything but hydrogen and carbon, you just spell out. You just put the it's only hydrogen and carbon that you don't have to put the symbols for. And that's because like 90% of your structures are just going to be hydrogen and carbon. So. The specific arrangements for atoms connected by specific types of bonds tend to react in characteristic ways. These structural components are going to be called functional groups because they tend to have sort of similar function. Okay, so you may have actually heard of these functional groups. You have, I'm sure. Alcohol, right? Everybody's heard of alcohol. There's special tax code and nutritional label codes for it. So, alcohol. You actually know others, though, like ether. That's what you're thinking of when you're thinking of fruity. Okay? Molecules' reactivity is going to be governed by these functional groups. These carbon chains are mostly kind of act similar and don't do a lot of different stuff, though some of them have a little bit of function. But it's usually the functional groups that have a majority of function. Okay? There are going to be several functional groups. Each are going to have their own functional group name. Compounds consisting only of carbon-carbon and carbon-hydrogen single bonds are going to be called alkanes. Alk, see that alk part? That means I don't care how many. Okay? I'm not specifying the number of carbons right now. That's what that means. When I want to specify the number of carbons, I'm going to change the alk part for a root word. Okay? These root words are going to be basically the normal Latin Greek you're used to, kind of mixed every few now and then. You guys all know the months are actually also. Like we're in September. Guess what month that was supposed to be? 7. Yeah. Yeah, the Latins did it the correct way. And then when it transferred over to other people, they just like added some extra months in there at the front of it and messed the whole thing up. But that's why September, October, November, December, right? So if you ever forget the last part of it, that's the easiest way to do it. But I'll do a little bit more on that. So again, this is an alkane right here. These are some of the different functional groups. This is an alkyne. Everybody say these with me. Alkane. And come on with me. Alkane. Alkyne. That's with the Y. Hear it? Alkyne. I'm going to tell you right now that this is a really, it's not necessarily fair, but it is what it is. How you say things and how you present yourself are going to be taken into account by people that judge you in the first perspective, right? And oftentimes will limit your ability to do things in life, okay? Sometimes you get a second chance, but not always. And so everybody that has a semi-Southern accent, semi-Tennessee accent is going to suffer a little bit this, because ein and een for all of you is the same damn thing. Okay? And that's why I'm making you do this. Okay, everybody ready? Alkene. Say, hear the een? Een. Okay? That's a double bond. Okay? And seriously, when you're doing these, look them up, how they sound. I'll mispronounce them every now and then. I'll mispronounce something, okay? It's inevitable because I cover so many things, right? You don't normally cover hundreds of functional groups on one Go. Like you work with 10 or 20 functional groups and you have that. But when you're first introducing these, actually say them, because if you never say them before, you're going to get to like graduate school or medical school or PA school, and people are going to make fun of you and go, yeah, that was dumb. And it's not fair sometimes. Doesn't mean you don't know more than them about certain things, but it is what it is, right? Okay. Everybody okay with that so far? So these are the different functional groups you'll see. We'll go in a bit more detail. That's actually what the IA and IB and stuff are mostly for, is naming. Okay, now organic molecules are going to be found exclusively in living organisms. Are going to be called biomolecules, and that's what you've probably heard of before in biomolecules. There's going to be 4 major classes of biomolecules that are the most common to encounter. There are proteins, carbohydrates, nucleic acids, and lipids. You notice that's also metabolically the things you probably talked about. So, yeah. There are other things, by the way, in living organisms and biomolecules, but we've covered like 90-something% of the amount of stuff you guys have intake, and so that's good enough for there. Okay, and so let's talk a bit about proteins and amino acids. This is going to be a typical alpha amino acid right here. Note that this part right here is your side chain. See that R? Okay, that denotes side chain. Anybody know what the R stands for? Residue. Yeah. So it's everything else but the structure I'm looking at. Okay. It can be anything over there. In this case, it's a side chain to amino acid. There are a bunch of different side chains to amino acids. I won't go into a lot of detail. You can do biochemistry and get lots of that. Yeah, a lot more than you want, probably. So this right here is actually the monomer for what a polymer that we typically call proteins or polypeptides. Okay. And so polymer means it is repeated units of that monomer. Okay. And so right here we have the amino acid. Note it's just repeated linkages. These are called amide linkages. That's the functional group you're seeing right here. It's that nitrogen oxygen portion right there. Okay, so those give you your two-dimensional, your one-dimensional and two-dimensional structures for your proteins. Specifically, this would be the one-dimensional I'm showing you here, okay? And these are going to then combine together to give you a three-dimensional structure. This right here in this case is a fibrous protein, okay? These are going to go together to give you an overall organ structure, which in this case is muscle tissue, okay? And then they combine together and give you living organism, right? Yeah. All right. I typically go up to here, by the way. I don't care about this part. Yeah. Just put them in a bag. Whatever. Yeah, that's because I do biochemistry. I don't teach it here. Dr. Phillips teaches biochemistry here, but I have taught biochemistry like 15 years. Very places, so I do know some biochemistry. All right. So this is referred to as a alpha amino acid. It's actually referred to as an alpha amino acid because it has that carbon right there. And so this position, this next position from a functional group, this is a functional group right here. This is the amino or amine functional group. Okay. This right here is the carboxylic acid. That's where the acid part comes from the name. Amino acid, right? Amino acid. These are two functional groups. The next carbon over from a functional group is called the alpha carbon. The one after that would be called the beta carbon. After that would be gamma. After that, delta. After that, nobody cares. We're chemists. We don't count past 4. Okay. So nobody cares. No, but it is the next Greek letter, but you will never use it because nobody cares. So it's just, yeah. This is the side chain right here. That's the residue, capital R. If you had more than one thing you had to denote, this would be R prime, R double prime, R triple prime. Okay, to denote that they're different. This right here is your different naturally occurring amino acids. There's 20 of those. There's actually a bunch of artificial amino acids now, and there's mirror amino acids now. So there's been a lot of research. In case you're wondering, the biochemistry field, taken broadly, doubles in number of publications every about 4 months or so. Yeah. Yeah. Nobody can keep track of it anymore at all. Like, it's absolutely impossible. So, probably why AI is being invented. Probably why. Okay, so this is alanine, leucine, proline. I'm just going to give you guys this because you don't really need it a lot for this class. However, these things are highly interrelated to organic chemistry, okay? And so we will talk about these every now and then. These are the amino acids. These are their side chains right here. See how they're black color or red color? This one actually wraps back onto the amino acid structure. That's the nitrogen, carbon, and carboxylic acid right there. So it actually wraps back and bonds to the nitrogen. Okay? And that's why P for proline. Anyways, so tryptophan, valine. These are the non-polar ones. See how they're non-polar overall? They don't have any charged poles overall, dipoles, for the side chain. Not the amino acid. The amino acid definitely does. Over here, we have the polar amino acids, and then these are the acidic ones and basic ones. So at physiological pH, these ones are acids. At physiological pH, these ones act as bases. Okay? Anybody have any questions about that so far? Anyways, you'll get a lot more of that in biochemistry. I think pretty much all of you are going to go off and take biochemistry at some point. Yeah. So have fun. All right. Carbohydrates. These are going to be called saccharides as well. They're going to serve a variety of biological functions. Carbohydrates can be characterized by their chemical composition. Right here we have ribose. You guys may recognize that. Have you ever heard of that before? Okay, like ribonucleic acid. Guess what that's made out of? Ribose. Yeah. Anybody know what? DNA. It has lost one of the oxygens on the ribose. Yeah. Okay, so this is glucose. This is 99% of the sugar you actually use in your body. It is not straight chain, though. It's typically in the form of the ring. And we'll work our way through into getting those functional groups and understanding those better. This is fructose, by the way. It actually has a ketone in it, which is the functional group there. That functional group is an aldehyde. That one right there is alcohol. And you'll notice that, oh my goodness, we're like explaining things you'll need for the next class. I know. It's like this class builds up to biochemistry somehow. Okay, so let's talk about the size hierarchy of carbohydrates. You will notice that the carbohydrates have monomers. These are the monosaccharides. They can be combined into disaccharides, which would be two of these. This is actually the ring structure right there, by the way. They react to themselves, forming ring structures. Glucose exists about 99-ish%, 98, high 98s, sometimes low 99%, as the closed ring form in serum. Okay. This right here is a polysaccharide, poly meaning many, so we just have many monosaccharides linked together. And this can make things like cellulose. So we have cellulose here, making strands that then build up plant tissue. Ooh, ah. Okay. Does anybody know what's typically you see these as in humans? What the polysaccharide you normally see is? That's actually. The polysaccharide would be glucagon or glycogen. The stuff around your liver. You know how you get a hard spot right here? If you've ever seen anybody that has a beer gut, how you get like a hard spot right here? That's because it's not actually fat. It's hard because it's actually a polysaccharide. Yeah. It has more to do with like starch than it does with fat. Yeah. Anyways, again, I'm just doing very broad, loose terms. You'll get more in biochemistry. A little taster here. Nucleic acids and nucleotides. So this is actually a nucleotide right here. Notice that it actually has three components. We have our base, we have our sugar, and we have our phosphate. Okay, and so that's our nucleotide. They actually are the monomers, which build up into polymers, and we call those double helical DNA in this case. Notice that the monomer polymers are actually one of the helices. You double it to make double helical. Okay. This DNA is actually not how the majority of your DNA is kept in your body. It's actually kept right here, where you have it wrapped into chromosomes. Usually, unless you're dividing, you actually have little pockets of it that are sort of unraveled a bit and being used. Okay. But if you actually stretched it out, you wouldn't be able to fit a DNA in your body. Forget the cell. And so, yeah, this is going to be what stores your genetic information. RNA is very, very similar to this, but little snippets usually, and usually only one strand, not bundled up. And so the RNA is how you typically translate it. And that's what you go into your proteins from usually. Okay. You can also use that as enzymes in case you're curious. Yeah. Yeah. Anybody have any questions? Did anybody see the most recent studies on metaphase cell splitting? You do not actually have to have round cells to split. They can split in several shapes, actually, but oblong shapes can split. Yeah, which is pretty wild. I know, a long time that rule stood, and then it got smashed about 3 weeks ago. Yeah. So all nucleotides are going to have three distinct components. We have the inorganic phosphate. So you have a little inorganic phosphate in you. That's a little weird, isn't it? Didn't think you were inorganic, did you? Yeah. Cyclic monosaccharide, that's your sugar. That's the ribose. And then a nitrogenous base. Note the nitrogens in the structure of the base. That's what makes it nitrogenous base. And that's overall what that looks like. That's a more complete structure of it right there. Notice this one has an OH here. This one has a hydrogen here. Guess what the one without the oxygen is? Yeah, deoxy DNA, right? Yep. So this is the DNA version. This one right here is the RNA. Okay, nitrogenous base is the DNA RNA. There are four nitrogenous bases of RNA. There's uracil, guanine, adenine, and cytosine. These are abbreviated, obviously, U, G, A, C, respectively. There's DNA then has GAC, and then it has thymine instead of the uracil. Okay. And so your nitrogenous base actually does change for U and T between DNA and RNA. And so here's uracil, here's the thymine right there. You can see that they're very similar functional groups and structure-wise. The only difference is this is methylated. Okay, it actually makes it slightly more stable, supposedly. I guess that is more stable, so it ended up in DNA. Anybody have any questions about that part so far? Okay, we are going to go ahead and start on the next chapter. We'll get like 5 minutes in. So, yay.